Our today's discussion is on simulation of single-stage single-phase solar photovoltaic inverter using MATLAB. This is the basic schematic of a single-stage single-phase solar inverter. The output of the solar array is directly connected to the inverter input. LCL filter is used to filter out the harmonics in the grid current. Now I will give the specification of the complete system. Open circuit voltage of the PV array is 493.5. Operating voltage range is in between 400 and 500. The switching frequency of the inverter is 10 kHz. Value of filter inductor is 4.06 mH, 4.35 mH, and filter capacitor is 6.23 microfarad. Grid voltage is 230 volt RMS at 50 Hz. Rated power of the system is 2 kW. This is the complete controller block diagram of a single-stage single-phase solar inverter. I used PI controller for the voltage loop, and PR controller for the current loop. You can read the reference paper to understand more about the working of this controller. I will leave the link for the reference paper in the description. Now we open the MATLAB and start doing simulation. First add a solar PV array. Set number of series and parallel strings for 2 kW rated power. Select the module type from the list. Now I will show you the VI curve of the selected array. This is the MPP point corresponding to 1000 irradiation level. And this is for 500 irradiation level. And this is for 100 irradiation level. This is the open circuit voltage of the array. And this is the operating voltage range. We need to check this box. Add a constant block. Set irradiation 1000. Set temperature 25 degree. Add a series RLC branch. This is the input bus capacitor and set its value 600 microfarad. Set initial capacitor voltage, which is same as the open circuit voltage of the array. Add a voltage measurement block. Add a go-to block. Name the voltage as VDC. Add a MOSFET. Form the single-phase inverter bridge using the MOSFET. Adder from block. Name it as PWM1. Name it as PWM2. Name it as PWM3. Name it as PWM4. Add a current measurement block. Add a series RLC branch. This is the inverter side filter inductor, and set its value 4.06 mH. This is the filter capacitor, and set its value 6.23 microfarad. This is the grid side filter inductor, and set its value 4.35 mH. Add an AC voltage source. Add a voltage measurement block. Add a go-to block. Name this current as I inverter. Name this current as I grid. Name this voltage as V grid. Now we generate alpha-beta voltage waveforms. Add a first-order filter block. Set its time constant, 1 by 2 pi into 50. Add a gain block. Set its value to. Add a go-to block. Name this voltage as alpha. And name the original grid voltage as beta. Now we build the phase-locked loop. Add a constant block. Set its value 0. Add a mux. Set number of input as 3. Add an alpha-beta to DQ0 transformation block. Add a demux. Set number of output as 3. Add a sum block. Add a PID controller. Set its Kp and Ki values. Add an integrator. Add a FCN block. Type the expression cos U1. And here type the expression sin U1. Add a go-to block. Name it as cos omega t. Name it as sin omega t. Now we start building the MPPT blocks. First, add a bus selector. Add PV voltage and current into the bus. Add a unit delay block. Set its sample time 1e raised to -4. This is the MPPT block, which I have been discussing in many of my previous videos. So I used the same block here for the simulation. You can watch the previous videos to understand more about this MPPT block. Here I have made two changes. Vref max changed to the open circuit voltage of the array which we are using here, and also, Vref init changed to the MPP voltage of the same PV array. Now we add the voltage controller blocks. First add a sum block. Add a product block. This block is used to compute the solar PV power output. Add a PID controller. Set its Kp and Ki values. Add another sum block. Add a gain block. Set its value to by 325, where 325 is the peak value of grid voltage. Add another product block. Add another sum block. Add a gain block. Set its value 400. Add an integrator. Add another gain block. Set its value 10. These all blocks are part of PR controller. Add another product block. Add a relational operator. Add a gain block. Set its value -1. Add a repeating sequence. This is the carrier signal used for PWM generation. I'm using 10 kHz triangular signal as the carrier, with amplitude -1 to 1. Add a logical operator. Connect all PWM signals to the gate terminal of each MOSFET. Now add scope to view the result. Add grid voltage and current to the scope. Add another scope and add grid current to the scope. Add a power guide block. I'm using fixed step solver type with step size 1 microsecond. Add a display block. Here we can see the output power generated by the PV array. Set simulation time 3.5 seconds. I forgot to change the parameters of the AC voltage source. Set its peak amplitude 325 volt and frequency 50 Hz. Now run the simulation. Here you can see how the power is climbing to the MPP point. It has already reached the MPP level corresponds to 1000 irradiation. Now we will try to change the irradiation and see how the power output changes. When I made the irradiation half of the original value, power also becomes half of the original value. Similarly, you can try different irradiation levels. So whenever we change the irradiation, power is changing to the corresponding MPP value. Now I will show you the voltage and current waveforms. This is the grid current generated by the inverter. Here you can see both grid voltage and current. Clearly, these signals are aligned in phase with each other, which means we are sending active power to the grid. Now I will try to change the irradiation level gradually. For that, I need a repeating sequence interpolated block. Set the output and time values. Initially the irradiation will be 1000. When the time reaches 0.5 second, it starts decreasing. When the time reaches 2 seconds, it starts increasing. And it reaches back at 1000 when time reaches 3.5 seconds. Now we connect this block to the PV array. Run the simulation again. Here you can observe the changes in the grid current with respect to the change in irradiation. The current was constant till time reaches 0.5 seconds. Then it started decreasing. Once it reached 2 seconds, it started increasing. So this is how the grid current is changing with respect to irradiation. And this is the current waveform. This is the end of this presentation. Thanks for watching.